Greetings, welcome to this video. In this video we're going to be looking at the principle of virtual work, and specifically our goal is to use the principle of virtual work to compute deflections in beams and trusses. But before we do that, we're going to have to go over the theory a bit and get an understanding of where these ideas came from, this idea of virtual work. So we're going to have to understand concepts of work and strain energy. So that's what this video deals with. We're going to be going over these concepts, and specifically work is called big W, strain energy, big U, and we're going to derive the principle of virtual work equation for trusses. And then we'll just kind of assume that the one from beams came from a similar place. So here I've shown this truss member, which is, as you know, a single force member, can only carry force along its axis. And the work done is by this force P that I'm pushing at the top of the roller. The displacement as a result of P must be in the same direction for it to be considered work. As you may know, work is defined as force times displacement. In this case, the work I'm doing on this truss member is from the force P, and the displacement, the corresponding displacement, is lowercase delta. So if I want to figure out the full amount of work done, I'm going to integrate from when I wasn't pushing on the structure to the point now at which I'm pushing with a load P, and that will give me this triangular shape if I integrate it. W is P times lowercase delta over 2. The formula looks different if you're applying a moment to create an angle change. So generally the work expression is P times delta, but it could be M times some angle, theta. The important thing to remember is that a point load tries to displace a structure in X or Y, and a moment at a location tries to create an angle change. Now work is a form of energy, and the energy or the work that's going into the structure is stored in the structure in the form of strain energy, so deformations. And we can relate these two because they're equal. Whatever we put in is what is stored in there. So this is called the conservation of energy. This is one of the ways we can state that. So W equals U, your external work done on the structure, is equal to the internal strain energy stored in the structure. And just how we plotted the work being done, we can also plot the deformation being stored. So the internal force in this truss member is F, and the deformation is big delta L. So we can say, similar to the W equation, that U is F times delta L over 2 from the time that we aren't doing any work to the time that we're pushing with the load P, and we have created this displacement small delta and this deformation big delta L. We know from an axial loaded bar that delta L can be equated to FL over AE. So we can write U is F over 2 times FL over AE if we like. If we equate this to the work done, we come up with this equation. P small delta over 2 equals F squared L over 2AE. You can eliminate the 2's, and then we're left with P small delta equals F squared L over AE. And this equation is useful. It can be used in the real work method, and also it's used in Castigliano's theorem. So these are both energy methods that we can use to compute displacements, but neither of them are really as good as the virtual work method. And that's why we're learning this. It's very powerful. Okay, so hope you're ready for a good old-fashioned derivation. Now, there's no need to really be scared of this one. We're just going to be using a bunch of shapes to find an equation, and it's actually pretty cool in the end. So let's start by drawing this thing we call the P system, or the real system of loads. And on the other side, we'll have the Q system, or the virtual system of loads. But let's first focus on this P system. So as you recall from the previous slide, we can take this truss member, we can subject it to a load P at this top roller, and it creates a displacement, delta P, and an elongation, delta LP. Now for some reason, we've chosen to use deltas for both these deformations. Well, one is a displacement, the other is a deformation. And it's kind of confusing, but oh well. So we can label this work plot and this energy plot just as we did before. But in this case, we're going to include the small subscript P, signaling that this work is done by the real force, the load P, and so is the energy. It's stored due to the load P, and the deformation and the elongation are all as a result of P. And we can equate WP equals UP. Moving over to this Q system, this is where things start to get a little strange. So we're going to apply a load in the direction of the displacement we want to compute. What we're really after is this small delta P on the left side. But we're going to apply this Q on the right side. And we're going to choose a value for it. Typically we choose 1 kilonewton or 1 kip. But the key thing about Q is it must be in the direction of the desired displacement, delta P, as we said. But it can be any value you want. The equations will still work out. And in the bottom here, very similar to the left side, we have this work done by Q and the U done, and the energy stored as a result of Q. And we can say that WQ equals UQ. So my advice here would just be to maybe pause the video and just look at what we have here and make sure you're good with it. So make sure that all these labels on these axes, the Q, the delta Q, the FQ, the delta LQ, make sure it all makes sense. Flip back to earlier in the video if you need to. And as usual, comment when I make a mistake, I'll say, because it's not an if, it's a when. Okay, so moving along. I've written here on the left side, or shown here on the left side, everything from the previous slide. So there's no reason to move back in the video. You might have to make the video big on your screen because there's some little writing. So we have the P system, the Q system, and now we're going to make a P plus Q system. So we're going to combine the two. So our force is now F total is FP plus FQ, our force in our member. And we can see in the work and energy, strain energy plots below that we've actually applied load Q first and then load P. So we have these triangles kind of stacked up on one another. And we can label these different areas in the triangles. So we have our WQ and our UQ as before, and our WP and our UP as before. But now we have this rectangular area, which I'm going to call WQ star and UQ star. And these two areas must be equal. Why? Because those shaded areas didn't change size, and we already said they were equal from before. So what is this WQ star, for example? Well, WQ star is the work done by Q over the displacement caused by the real load P. So this is kind of a strange thing that Q can do work that it's really taking credit for some of the displacement that P caused, but because it's pushing there, it's still considered work by the definition. So we can write WQ star is Q times delta P. Just looking at the area of the shape there, it's a rectangle, Q times delta P. And recall that delta P is our desired value, right? That's the value that we really wanted to compute here. So our strain energy, UQ star, we can say is FQ times delta LP. Again, just a rectangular shape. Putting these together, we can write that Q delta P is FQ delta LP. And recalling from earlier that an axial loaded bar has a delta LP of FPL over AE, the subscript P just saying the P is causing the F and the delta LP. We can sub this in, and then we'll just add this little summation symbol, being as there could be more than one member, and there often is in a truss, for example. So if you blink too fast, you'll miss it, but we actually just wound up with a meaningful equation. So let's take a look at that. We have our Q, virtual load, which is generally chosen to be 1 kilonewton or kip, and our real displacement, delta P, the value we're after. And we multiply those two together, this equation is telling us that's equal to our member force due to our virtual load Q, or FQ, and times delta LP, the real deformation. And this real deformation, we know it's real because it has a subscript P. Everything with the P's is real, everything with the Q's is virtual. This real deformation could be due to a force, as that's the case that we've been looking at, but it could also be due to a temperature change or a fabrication error. All these result in members getting longer or shorter. So I've written the equation that we derived in the bottom left corner here. And this was for a truss subjected to real forces, or a real force P. But more generally, we can write the following. The sum of all the Q's times delta P plus delta sup, or support, equals the sum of FQ times FPL over AE plus alpha delta TL plus delta L fab. So that was a bit of a mouthful. So let's link up all these terms with what they're caused by. The FPL over AE is from a force, as we know. The temperature produces a change in length of alpha delta TL. And the fabrication error is just simple. It's just how much longer was the element than it should have been, delta L fab. On the left side, we have this new thing that we have to introduce, this delta support, or delta sup, or whatever you want to call it. And this corresponds to a support settlement. So this equation is that robust, it can even consider support settlements on the left side here. We didn't derive it for that part, but it's kind of intuitive, I guess you could say. But not until you've done examples. Examples are what makes everything make more sense. So that's what we're going to do next, some examples. And thanks for sticking with me throughout this video. All right? Example time.